Let's add the electric force in 2 dimensions now to make things more interesting and a little bit more realistic. So far, we've only looked at the force between charges on a line. If we have 3 or more charges that do not fall on a line, we must add the forces just like we added vectors that were at angles to one another. We've already done that with kinematics, dynamics, and momentum problems. So here we go. We're now working in 2 dimensions. First, establish perpendicular axes that are symmetric to whatever problem we have. Calculate the force on the charge at point C from the charges at point A and point B on the below diagram. The charges at each point are equal to positive Q. We have a triangle with 3 equal sides. There you go, there's R again. Remember, R doesn't have to be a radius, it can just be a distance or a displacement. What is the value of theta? And while you're thinking about that, let's also choose some axes for the problem to take advantage of the symmetry of these charges. Alright, first answer. We have an equilateral triangle, so each angle, theta, is 60 degrees. And since we're interested on the force up here, we're going to draw a Cartesian coordinate system centered on point C. Since the charges at point A and B are equal in magnitude, the force that A exerts on charge C is exactly the same in magnitude as the force that B exerts on charge C. The next thing we have to do is resolve f of AC and f of BC, magnitudes of which are equal, into their components. Look at this. I've already labeled these angles theta. Why? How was I able to do that? Well, let's see. Let's extend this line out here. So this line connecting A and B is parallel to my x-axis here. And note that this angle theta is the same as the angle here. And by the corresponding angle theorem, they're the same. So if this is 60 degrees, this also is 60 degrees. We resolve each vector into its x and y components. And we know that since force of BC equals the force of AC, and that these angles theta are the same, we have to have the magnitude of ACY equal to BCY, and the force of BCX equals the magnitude of force of ACX. So what happens in the x direction? Well, these two guys cancel each other out. There is no force in the x direction. How about in the y direction? Well, they're both pointed up, so they're not canceling, so we have to add them together. So now it's time to do the numbers. The vector resolution we did over here gives us the direction of the forces. So we've already stated how the x components are going to cancel out, and the y components are both in a positive direction. They're both pointing up. So when we calculate, FAC is equal to F of BC, and that just equals the force. We're going to get rid of the subscripts here because they're equal. The force in both cases is K, we use Coulomb's law, times the 2 charges, they're equal, divided by R squared. Right? The distance here is R, the distance here is R. So our total force due to the charges is going to have a magnitude of KQ squared over R squared. Let's look in the y direction. It's equal to the force of AC in the y direction plus the force of BC in the y direction. So let's just look over here. What is this guy equal to in terms of this force right here? Well, it's going to be the hypotenuse, which is the force, times the sine of theta. So there we have the force of AC times the sine of theta, plus the force of BC times the sine of theta. We know that force of AC equals force of BC equals F. So we have 2F times sine theta. We plug in the value of F, KQ squared over R squared, into right here, F. We now have 2k q squared over r squared times the sine of the angle, which we found to be 60, and we get this answer here. The x-axis, as we already alluded to, is going to be 0, but let's do the math anyway. We have AC is going to be a positive cosine theta, FAC times cosine theta in the x direction, and in the x component due to charge B will be negative because it's in the left going to the left. So that's minus FBC cosine theta. We know that FAC equals FBC equals F, so they cancel out, they're equal to 0. So the total force on charge C in this configuration is in the y direction. You have to specify the direction, and its magnitude is radical 3 times k times q squared over r squared.